Hello everyone, today in this video we'll be discussing the module 4 of microcontrollers and we have the following topics. This is related to the exceptions, interrupt handling and firmware. Okay, so we'll be discussing the important questions and what all you need to know to score more than 80% marks in the exam. And before starting, please do like and subscribe. It helps me make more videos like this, and if you have any questions you can DM me on Instagram. The first topic is exception handling. Okay, do you know what is an exception? Exception means normal something will be going on, the routine will be going on, in between something will happen, that is an exception. Okay, that is which is not expected. Okay, so in software also the program will be running, in between something will happen so that the program execution will stop and that something will be taken into consideration and that will be over and then it will resume its execution. That is called as exception. Okay, and we need to handle exceptions, otherwise what will happen, software will not resume and it will be stuck there itself. Okay, that is a useless system. So an exception is a condition that needs to halt the normal execution of the instructions. Okay, examples are when the ARM core is reset. Okay, when the reset happens, at that time it's an exception, the normal execution needs to be halted. When an instruction fetch or memory access fails. Okay, when it fails, that is an exception. When an unidentified instruction is encountered, when a software interrupt instruction is executed, or when an external interrupt has been raised. So exception handling is the method of processing these exceptions. Okay, the way in which we handle this exception is how do we process when an exception comes, what we need to do, that is called as exception handling. To handle the exceptions, exception handlers are used. Okay, it is a software routine that executes when an exception occurs. Okay, so exception handlers, they are trained to handle the exceptions. Okay, so we'll be learning more about it. ARM processor exception and modes. Okay, so there are different types of modes. First one is fast interrupt request. Okay, what it does, it is used for fast interrupt request handling. Okay, the interrupt request has to be handled fast, we will be using the fast interrupt request handling mode. Next one is interrupt request. Okay, interrupt request is a normal interrupt request. SWI and reset. Okay, it is a protected mode for operating systems. SWI means software interrupt and reset means when the system is restarted. Prefetch abort and data abort. Okay, for why it is used, virtual memory and memory protection handling. Okay, to handle with the memory purposes. Prefetch abort means end. Prefetch means before itself you will end, and data abort means the data associated with that will end. Unidentified instruction, software emulation of hardware processors. If we are executing something which is not known to the system, it will be an exception which is undefined instructions. Okay, so this is the diagram. Also the reset is associated with SVC and the data abort is associated with the abort commands and so on. Okay, next we need to know about the vector table. Okay, vector table is nothing but suppose an exception has happened. Okay, like some fire has come inside the system. Okay, I'm just giving an example. Fire, like that, it is not an exception. Okay, fire comes, the system will be blasted. So if fire comes inside the system, what it needs to do, okay, the thing what it needs to do, that is written somewhere in the program. Suppose it is written in location Y, and another thing is there, if water comes inside system, what it should do, that is written in location X. And if the air come inside the system, it has to be done, it is written in location Z. Now X, Y, Z, whatever is written, that will be present in one table. Okay, if fire comes, it is written in X, if water comes, it is written in Y, and so on. So this table is called as the vector table, which denotes what will happen and what should be done. Okay, means if what happens, what should be done. Okay, that table is called as a vector table. So it is a table when ARM core branches to an exception is raised. Okay, branches to means it goes to that location whenever an exception is raised. Okay, so the addresses, the whatever is the X, Y, and Z, that is nothing but the address where it is stored. So the address can contain one of the following form. The direct address it can contain. Okay, the branch instruction provides a branch relative to the place from PC, means 5 locations from PC. Okay, PC means program counter where the program is currently executing, that point, and 5 locations from there you will find out the address where you have the solution for the exception. Or it will be LDR PC offset, means some location from PC you have to go offset. Okay, and then example is given here, 0x4ff0. Okay, it has to go 0xff0 hexadecimal, whatever the value is, that much locations from the PC. Okay, that is the address which we need to reach. Or move PC immediate. Immediate means the direct address is given, PC will be going to that location. Okay, so these are the different ways of writing the address. So the below table shows the processor modes. Okay, so the exception can be reset. So vector table offset is 0x00. It is written there itself what it needs to do. If it is an undefined instruction, it is written 4 places from the starting. If it is software interrupt, it is written 8 places, 12 places. 16, 20, 24, 28, like that it is written. Okay, so whichever the exception occurs, suppose that the data is aborted, where it should go to find out what it needs to do, it should go 12 40, if not 12, 16 locations it has to go to check what is to be done when data abort has happened. Okay, so this is a vector table offset. Next is exception priority. Suppose that two or three exception has happened together. Which one you will choose? You will choose your favorite one? No, that is wrong answer. Why? Because it should be handled based on priority. Which is more priority, that it should be handled. And the priority is assigned as follows. Reset is given the highest priority. After that comes the data associated exceptions. Okay, data abort will be the second position. Then we have fast interrupt and interrupt request. Okay, then it is related to abort. Abort comes in fifth location, and in sixth location we have software interrupt and undefined instruction. Both are here. Whichever is more, it will be taken into consideration. Okay, next we need to know about the link register offsets. Okay, so suppose that I was executing from here and I stopped at a point, I went and executed something else, then it was over, I have to come back here. Where will I know where it is stored? This will be stored in a register called as link register. Okay, this address will be stored in a link register. Okay, so when an exception occurs, the link register is set to a specific address based on the current PC. PC will be pointing to current location, and this will be stored in a link register, and then PC will be moving to the here, this place it will be executing, and PC will be here. Next PC has to resume from here, and this information is present in LR, so LR will tell PC move here, so PC will move here, and the execution will continue from here. Okay, that is the link register. And here also we'll be having the link register based addresses, how much we have to subtract to reach that location, and here is the information also, the use of it. Okay, so the return address we are calculating where it has to go. Next, an example of returning from IRQ or FIQ, interrupt request and fast interrupt request. So if you have got these two types of requests, you have to come back also. How do we come back? So to come back, you have to use the sub S instruction, sub S PC R14 4. Okay, so R14 is the register where it is stored, and we have to go 4 locations behind it. Okay, so to return to the original place. Okay, so it is directly referred from SPSR register, because if S is written here, that means it is SPSR register. That answer will be taken into the CPSR register. Okay, second topic is interrupts. Till now we discussed the exceptions, but now how exception happens? Exception happens because when an interrupt is raised. Okay, interrupt causes an exception to be raised. Okay, so interrupt is the main thing which comes first, then comes the exception. So a system designer who has to design how this interrupts will be happening, it is a system designer who can decide which hardware peripheral can produce interrupt request. Okay, not all hardwares can be producing the interrupts, only few of them can produce. So which of them can produce, that is decided by the system designer, and the decision can be implemented in hardware or software or both. In all of these three things it can be implemented. And interrupt controller is the one which is controlling the interrupt requests, and they are assigned based on different requirements. Okay, the interrupts which are there, it is assigned based on different requirements. For example, software interrupts are normally reserved to call privileged operations on the operating systems. Interrupt requests are normally assigned for general purpose. Okay, software is for privileged, interrupt request is for general. Fast interrupt request is required when it is when a fast response time is needed. Okay, and what is interrupt latency? Suppose that the time now is 1 o'clock. Okay, and 1 o'clock I raise an interrupt. Okay, and I waited in 1 2, the interrupt started executing. So the time delay between 1 o'clock and 1 2, that is called as interrupt latency. The point when I raise the request and when the request actually executes. Okay, so that is the interrupt latency. There are two ways to handle the interrupt latency. First one is using nested interrupt handler, means whenever an interrupt is going on, if another interrupt comes, start that interrupt also in between this only, and if another comes in between, start there only, and when it is over, then resume it from here, and when this is over, resume it from here, and when this is over, normal execution will be resumed. Second is prioritization. If 2 or 3 interrupt comes which is having the more priority, that will be given the consideration. Okay, next is interrupt request and fast interrupt request exceptions. Okay, when an interrupt request or fast interrupt request happens, ARM processor will continue executing the current instruction until it is over, and then the stage of the pipeline before the interrupt is handled. Okay, whatever is the stage of the pipeline it's doing, that will be over first, then it will take the interrupt. Okay, and when it starts handling the interrupt, CPSR is stored in SPSR, because CPSR will now be handling the interrupt requests values, and SPSR will be having the previous execution value, so that when it is over, it will again refer what CPSR has and copy paste in CPSR, so that current execution can resume. Okay, So as you can see, a diagram is given here. In here, we don't have any capital I. Capital I means interrupt. Okay, and when an interrupt happens, it becomes capital. I will become capital, and SPSR will store the CPSR values, and R14 will be having the program counter, which is the link register, and current program counter will be the interrupt requests place. Okay, that is 0x18. From there, it will handle the interrupt, and when it is done, it will again return to the user mode. Okay, and R14 is assigned the value of PC when interrupt was raised. Below image shows the flow of FIQ interrupt. Again, it is the same. The previous one we discussed is for IRQ. This one is for the FIQ. FIQ also same thing. It happens here. The F interrupt is raised. Okay, FI means fast, right? So interrupt and F both are made capital, and it is stored in SPSR, and other things are same only. And the software handler will handle the interrupt, and it will return to the execution, normal execution. Now we can enable or disable the requests also. So based on ARM's processor modification in CPSR, in privileged mode, we can enable or disable. How do we enable or disable? There are three steps. First is IRQ. If you want to enable IRQ or disable IRQ, what you'll do, you'll copy the values of CPSR, means this whole thing, in a register R1. Then what you will do, the register R1, you will apply a mask. Mask means it will keep all the other values same, and whichever value we want to change, that will be something like false or true, so that it becomes reverse, and other things will be remaining same only. Whichever the thing we want, that one we will change. In this example, it is 0x8000. 0x80, that means it is 1000 at the end. 1000 means it will take from here 1000, right? So I will become small here when it makes it as false, and F will become capital. Okay, so here also it's the same thing which is happening. If it is FIQ, it will take 0x40 because F has to be made capital. So it is taking the F small here, and F is becoming capital. Actually, it should be reversed. Okay, it is written in a wrong way. So enabling interrupt, you got the point, right? We are masking it. Masking means we are making that bit whichever is there, that only as capital or small, based on 1 or 0. Okay, so AND operation will be happening, or operation X or something will be happening, such that only that particular bit will be made from false to true or true to false. Okay, so that is the interrupt enabling. And disabling also will do the same thing. That's the reverse thing will happen here. Okay, now basic interrupt stack design and implementation. To implement the interrupts, we have to use a stack. Okay, so the to design the stack of an exception, we have to consider two things: the operating system requirements and the target hardware. Okay, and two design decision needs to be made. The location determines where the stack begins, and the stack size, how much it can go. Because if I know the location but I don't know how much it will go, it might be less only. So I also need to know where it's starting from and how much it will go, such that I allocate enough space for it. Okay, so to handle that, we'll be having the two memory layouts. Sometimes this is used, sometimes this is used. The difference is only one thing here. The difference is that here the interrupt stack is present, and here the interrupt stack is present at the top. Okay, these are the two typical memory locations. Both are used widely. Okay, and good design tries to avoid the stack overflow. Stack overflow means if I have assigned the stack value of 10 and 20 things come in between, then 10 things will be spilled here. So to avoid that, we have to use a bigger system, memory protection, and we have to call a stack check function. We have to check a stack before putting the items. If it is not having space, take another stack, right? So that is about the interrupts. Moving on to the third and the last topic, which is the firmware. Firmware is deeply embedded low level software that provides interface between the hardware and application. So this is the hardware, this is the software. In between we have firmware. Okay, so it handles both software and hardware. It acts as an API in between. Okay, and hardware will be having it will be calling the hardware and getting the information, providing to the software. Okay, so for that it will be using one system called as a bootloader. It is a small application that installs the operating system or the application onto a hardware target. Okay, it only exists up to the point the operating system is executing, and it is commonly incorporated in the firmware. So it is a part of the firmware. Okay, so what it does, so it sets up the target platform. Target platform setting up means program the hardware system registers, means the system register which are there, that is made as ready. Platform is identified where it has to be done, and diagnostic happens to analyze if there is any malfunctions. Then the debugging happens. There is an interface where you can see how much is the processor RAM used, what are the variables used, and whatever is happening, and you can add the breakpoints. So it allows you all the features to debug. After that, you can also give commands using the command line interface. This is the first step, setting up the target platform. Second is abstract the hardware. Abstraction layer means it will hide the hardware part from the software, so that only the essential features is seen, and device driver helps in doing that. Okay, The next one is load a bootable image. Okay, basic filing system. That means whatever is being performed in the computer that has an image. Okay, means that will execute that particular point of time whatever is written inside it. Okay, and these images are stored inside the disk. Okay, it is stored inside a disk, and that disk it will be loading whenever it is required. Okay, so that is called as bootable image. Okay, and relinquish control means giving the control. Okay, what it does is basically the PC is pointing to a new image. Suppose that I've run a program and now I require some new feature. Okay, so what I will do, I'll load the image of the new feature, and now when the image is loaded, the program counter should start executing what is in the image, right? So program counter should point to the place where the new image is. So that is what happens in the fourth step: alter the PC to point to the new image. Okay, so the more information is given here, you can go through it. Okay. Next is firmware suite. ARM has developed firmware package called as ARM firmware. Okay, ARM firmware suite will what it will do. It will be a package that includes two things: micro hardware abstraction layer, and second thing is a debug monitor called as Angel. Okay, so here what it is basically doing is it will be abstracting the layers and it will be helping us with debugging purposes as well. So micro HAL provides a low-level device driver framework that allows to operate over different communication devices like USB, Ethernet, or serial. And since we have got a low level device driver, we can call an API to handle the hardware level things and provide it to the software. Okay, it provides mainly these features: system initialization to initialize the system, hold serial driver to provide a basic method of communication, and LED support will be there to know what is the status of it. Okay, and the timer support will be there to context switching, or if you want the timer based execution, and interrupt controls will be there to handle the interrupts. These are the functions provided by the micro hardware abstraction layer. Okay, second thing is the debugging monitor. Angel allows communication between host debugger and the target platform. The communication between these two is provided by the debug monitor. Okay, and it uses the software interrupt instruction to provide a set of APIs that will allow a program to open, read, and write a host filing system. So what it does, it will cause an interrupt such that it will call some APIs to allow to open, read, and write to a host filing system. And the interrupts are used for communication purposes. Okay, and the example of that is the Red Hat Red Boot. Okay, Red Hat is such a tool which is developed by the Red Boot is such a tool which is developed by the Red Hat. It is a firmware tool. It provides open source license with no royalties or upfront fees. Basically what it does, it provides both debugging capability through NU as well as bootloader. Okay, both of these are required to initialize the system and debug what is the malfunctions in it. Okay, so it supports the following features: communication is present, ROM management, random access, random what is ROM's full form? Random object memory, and full operating system support. Okay, it will be giving us the full operating system support. So due to these three things, we'll be easily able to handle the firmware requirements. Okay, an example of implementation of the red hat is the red boot is the sandstone. Okay, what it is, it will perform some tasks that helps in initialization and debugging. So following are the tasks performed by the sandstone: set up a target platform. Okay, first thing is to set up a target platform where the things needs to be executed. Then load a bootable image. Okay, then image is loaded, and then relinquish control to the operating system so that it executes the image. Okay, and the following diagram shows the sandstone directly layout. It is in your system also. Okay, if you search sand.s, you will be able to see the following structures: make file, readme text, build and payload, slosh.bin, src object image log, and sand.sc. Sand.s will be present under src. Okay, this is the directive. If you want to go to the sand.s for initialization, you'll be able to go via this route. Okay, and it also has the code structure which is broken down into different series of steps. Let's discuss. So basically it has 5 steps. Okay, the code structure is divided into 5 serial steps. It happens one by one. Okay, and what it does finally, it will be able to execute the system in a new environment. Okay, so basically here what happens, take a reset exception. This is the first step. Okay, what it does, it is the first instruction executed, it causes all vectors to branch to a dummy handler. okay, and then it moves execution to the second stage. Okay, so our main goal is to move the old code to a new environment. Okay, so firstly we need to make everything ready, so all vectors will branch to a dummy handler, and then it moves to the second stage, and this is the code which will do that. Okay, and the results of the first step are dummy handlers are set up and control is passed to the initialization of the hardware. Now we have to initialize the hardware. It is the primary phase where initializing the hardware, and the main point here is to initialize the registers. Okay, initializing hardware means initializing the registers only. So but before we can set up the segment display, you have to display the base address of the system registers. Okay, once the system registers are present, we want a display also to display what is the status going on, and for this display you need an address where it has to start from. That address we have picked it up as 0x3 and so on. Okay, so what it will do, it will start from here and then it will be executing it. Okay, so the new location is set up. System registers are set from a known base address, and system display is configured to display the segment programs. Whatever the programs have to be displayed, it will be displayed in a system display. Third is to remap the memory. Now we have a new place where the displaying and the execution is happening. From the base address we need to remap the memory also, so that it will be close to where it is executing. So one of the major activities of the hardware initialization is to set up memory environment. After memory environment is set up, it will change the locations. Okay, so initially these were the locations, and using this code we'll be allocating a new flash ROM location, and after that there will be a jump happening from the base address to the new location, and after that the new location will look like this. Okay, so it will be executing from the new location. So result is memory has been remapped and the PC points to a new location. Fourth step is to initialize communication hardware. We have to communicate with the hardware, so we have to configure serial port and output the standard banner. Okay, whatever is happening inside the system, that is happening through the serial port and it is shown in the standard banner. Okay, banner is used to show firmware is ready or the status if it is not ready and it is executing, loading, whatever it is. Okay, so like this it will be shown what is the status, booting payload, and what is the memory remapped, what is the status, alive platform is E70, and so on. Okay, so this is the banner which it's showing all these things. Okay, and the fifth step is to boot a loader payload, which means copy the payload and relinquish control. Copy the payload means whatever is the data in the previous section, we'll be copying it and pasting it here, and relocation control means pointing the PC to from where it has to be executed. Okay, so this code does the following, and here what it does, the register R13 points to the beginning of SRAM, and the source register point to the start of payload. Now we have the beginning of SRAM, we have the payload also. So from payload we have to copy and paste to the SRAM. Okay, so it is copied into the SRAM. After that the control is given to the PC to start from where it is located, which is 0x00. So control of PC is relinquished to the payload PC 0x00. So execution will start from here, which is a new location. Okay, and finally it will also display the information in the banner. Okay, that's all for the module 4. If you found this video helpful, please like and subscribe, and thank you so much for watching. I'll see you in the next one.